So in the last video, we intuitively defined torque to describe how forces attempt to make things twist around. And we decided that was equal to the force times the lever arm, or what will be more useful here is the distance between the axis of rotation and the point of application and the tangential component of the force. So I know this thing that I've drawn here looks a little nasty, and I'll try to step you through it piece by piece. So just as a working example here, I'm imagining I have three point masses that have been tied together by massless rods. And each of these masses is feeling a force being applied to it. So I've drawn the forces in red, and I've also noted the tangential components of those forces. So let's just to make this a little clearer here, let's go look at particle 1. So if we look at particle 1, we can say that the force being applied on it is equal to m1 times a. And then what we can do is we can take the tangential component of this and say that F1 tangential equals M1 A1 tangential. And we remember from our explorations of angular acceleration that A1 tangential is equal to R times alpha, which R here, R1, because that's the distance from alpha to the mass. So this particular mass is going around in a circle like that. Okay, so how does this apply to a torque? Well, I can go ahead and take this and I can times it by R1 and get that this is equal to M1 R1 squared alpha, or the torque due to force number 1 is equal to M1 squared, M1 R1 squared alpha. Okay. So what is this telling us? Well, the force is also attempting to accelerate the mass this way, and it would, except you've got this massless rod here, right? And so in order to keep the distance fixed, the massless rod has to be providing a radial force out to cancel the radial force in. So this is where the whole business of looking at torques comes in super duper handy. These radial forces are due to intermolecular forces between molecules typically, and there are lots of them, and we really don't care about them. We only care in so much as we know that they are responsible for keeping the object from flying apart, and they are responsible for making sure that the mass goes around in a circle. And so we know they're doing their job, but we really don't need to model them. The bit that matters is going to be the bit that's side to side, that's actually attempting to change the rate at which the object is rotating. So here, by taking all these tangential components of forces, we get the appropriate tangential components of acceleration, and we can then say, oh, the torque due to this force is equal to this quantity here times the angular acceleration. So for our object, I had more than one force attempting to twist it. So the net torque being applied to the object will be equal to tau 1 plus tau 2 plus tau 3. So this is M1 R1 squared alpha, and you can get tau 2 and tau 3 in a very similar way. So this will be M2 R2 squared alpha plus M3 R3 squared alpha, and so forth. All right, so we can then rewrite that the net torque here We can pull out an alpha from everything, and you're left with m1r1 squared plus m2r2 squared plus m3r3 squared plus and so forth times alpha. And so what we'll do is we will define this quantity here in the parentheses. This is going to get its own special name. It's going to be called the moment of inertia of the object about the rotation axis. And what you do is you sum up over all of your particles. So sum over I, mi, ri squared. And this actually defines our moment of inertia. And you can see a typical units are going to be kilogram meters squared. So with that, I can divide both sides through by this moment of inertia and get that the angular acceleration is equal to the net torque over this moment of inertia. And this usually gets officially called Newton's second law for rotations, but I'm not a fan. I prefer saying it's Newton's second law applied to rotations, and this is why. We started with Newton's second law and applied it to each and every particle, and then we just added up the tangential components of all these second law expressions to get this. So this is nothing new. It's not a new law of physics or anything like that, but it's just distilling down Newton's second law with a very specific focus on how do we make things twist. All right, now calculating these moments of inertia get hairy. And again, for all but the simplest of cases, like say a few point masses attached with massless rods like I was showing you there, again, it will involve math beyond the scope of this presentation. However, really smart nerds have made tables of these things. And if you go and look in pretty much any physics book or you look online, you'll start to find things like this. Usually the way these tables are organized is they'll draw a picture of the thing they're interested in. So let's say we've got a long, thin rod of length L. They will then draw in the axis of rotation they're thinking about, say that, and then they will note what the moment of inertia is for this object about that specific axis. So for this long, thin rod here, the moment of inertia turns out to be 1/12 the mass of the object times the square of its length. And where you choose to rotate it matters. You can then go and look in these very same tables, and often in these very same tables, they will have also computed it for what if you twist it around the edge of the rod like so. And it turns out in that case, the answer is 1/3 ml squared. So it's the same object, but the contention is that it's 4 times harder to twist, because effectively we can think of this moment of inertia as describing how hard it is to twist something. Just like the mass says how hard it is to accelerate something, the moment of inertia says how hard it is to twist it. So the bigger the moment of inertia, the harder to twist. So here it's 4 times harder. You can try this with your pencil or pen right now. Try twisting it about the middle, and then try twisting about the end. It should feel about 4 times harder to twist it about the end than about the middle. And for rotationally symmetric objects, usually you only care about rotating the object through its symmetry axis. But the tables go on forever just in case you need something different. So if you go look up, say, a cylinder, they will dimension in a radius here. So they'll say radius R. And then what they'll say for this is that the moment of inertia for this is 1/2 mr squared about its central axis. And this would be different than for a sphere. For a sphere, same deal. Again, we're imagining doing it about an axis going through the center of the sphere. So something like that. When you look it up in the tables, you'll see that it says that the moment of inertia is 2/5 mr squared. So this is 0.5 mr squared. This is 0.4. So it's a little easier to twist a sphere of the same radius than it is a cylinder. Now, why would that be? Well, if you think about it, the only way they can have the same radius and the same mass is if the mass is more concentrated in the sphere, and specifically that it's more concentrated about the axis of rotation. Same thing happened here. Here, when the axis of rotation was here, the matter is more concentrated towards the axis of rotation than it is here. The more concentrated the matter is towards the axis of rotation, the lower the moment of inertia. The less concentrated it is about the axis of rotation, on the other hand, the higher the moment of inertia. So this is something that archers are well aware of. If you go and look at a photo of, say, an Olympic recurve bow being shot, you'll notice these very long carbon fiber rods sticking out from the bow. These rods get called stabilizers, and they serve a couple of functions. One of them is to help damp the shock associated with the shot, so as to make it feel a little more comfortable and make you less likely to flinch in anticipation of the shot. But if you notice, at the end of these rods, there are masses at the end of these rods. And what that's doing is you had a very lightweight rod that put not that big of an amount of mass way far away, maybe a meter, maybe more, away from the pivot point of the bow, where it comes in contact with your hand, thus making it very hard to twist the bow. So anyway, now let's go do an example of a couple of examples of this. So we'll start first by just thinking about a teeter-totter. So let's say we go and look here. Let's say you have two kids in very different grades. They're attempting to play teeter-totter. So you got the big kid over here. He's really happy because he's going to be launching the skinny little kid into outer space, or so he thinks. Now, the teacher sees this and decides that in order to make it fair, you should move the fulcrum so that the two kids will balance in order to make this more fair. All right, so let's say this kid has a mass of 50 kilograms here, and we'll say this kid has a mass of 25 kilograms here. Let's say this is a very long teeter-totter plank, like so. And so we'll say this distance between the fulcrum and the big kid is 1 meter. And what we're interested in finding out is the distance between the fulcrum and the skinny kid. And just to make things less awful on ourselves, let's make the plank massless. So we can go ahead and make our system the kids plus the plank. That will make it a little easier to think about. So we can go ahead and do a force identification diagram here. So we've got one contact force. That'll be the normal force from the teeter-totter being applied from the fulcrum being applied on the plank to keep the plank from crashing through it. And this time we have two long-range forces. We've got the force of gravity on the big kid and the force of gravity on the little kid. All right, so now where things are different here is that now when we're thinking about rotations, we need to draw what's called an extended free body diagram. So with an extended free body diagram, usually what you end up doing is drawing a cartoon of the situation, like so. So we'll draw in the plank and the kids here. And now what you do is you go ahead and apply the forces draw the forces at their points of application. So force of gravity 1. Oops, this one won't be as long of an arrow. In fact, it'll be half the length. Force of gravity 2. And then right here where the pivot was, we will draw the normal force, which will actually be the biggest of them all in this problem. Okay. So we need to label our axis of rotation. When we get, this is technically an equilibrium problem. When we get to treating equilibrium problems more carefully, we'll find out that there's a lot of freedom in choosing the axis of rotation. But for now, let's just go with the obvious choice of the fulcrum. So then we can go ahead and label our lever arms like so. So, and again, here, the lever arm for the normal force is 0 because the line of action goes right through the axis. So there will be no torque due to the normal force. So we can start with Newton's second law applied to rotations here. The angular acceleration is equal to the net torque over the moment of inertia. Now in this case, the angular acceleration is 0, so we can put that in right away. So we can then go ahead and times both sides through by the moment of inertia and get that the net torque is 0, which is good because now we don't even have to calculate the moment of inertia in this particular case. So we've worked out that this will be the torque due to kid 1, gravity on kid 1, plus the torque due to gravity on kid 2, plus the torque due to the normal force. That has to equal 0. And the torque due to the normal force is itself 0. All right. So now when we write down the torques, remember, unless we say otherwise, that counterclockwise is positive and clockwise is negative. So let's look at the first kid. Is the first kid trying to spin the teeter-totter clockwise or counterclockwise about this x right here? Well, counterclockwise. So the force of gravity due to this kid is applying a positive torque. So this will be equal to Fg1 times r perpendicular 1. I guess I should actually say R1 perpendicular. I'll fix that right here as well. So R n perp, 1 perp, 2 perp. There we go. And that's it for counterclockwise torques. So now let's look. The little kid here is attempting to twist the teeter-totter clockwise. So that'll be negative. And again, it'll be Fg2 R2 perp. And that'll equal 0. All right, now in this case, the perpendicular distance is just R1 and R2. If the teeter-totter were tilted, that would be different, but here it's not. All right. So we can go ahead and solve this for R2. So add that to both sides and then divide by Fg2 is going to give me Fg1 over Fg2 R1. So this will be M1G over M2G R1. Cancel, cancel. Hey, isn't that interesting? Everywhere in the universe, the game of teeter-totter is played exactly the same way. So this will be 50 kilograms over 25 kilograms times 1 meter gives me 2 meters. And that makes sense. We all know from our practical experience the skinny kid should be put twice as far away as the bigger kid. All right. Let's do maybe a little more complicated of an example here. So let's say you've got yourself a big disc here. Let's say this disc has a mass big M of 10 kilograms. And it's a big disc, so let's just say the radius is 2 meters. And we're going to tie a string around it, or wrap a string around it, and we'll hang a smaller mass, let's say 5 kilograms. And this disc is attached, this is all vertical, this disc is attached onto a axle here. It's free to spin. And what we want to know is what is the acceleration of the little block here. So here, we're going to have to analyze it a couple of different ways. For this little block, just using Newton's second law makes all the sense in the world. Now for this isn't going to be moving, it's just going to be spinning. So using Newton's second law applied to rotations makes more sense there. So let's go ahead and follow that through. So let's go first and do this bit here. So again, force identification diagrams, there's a force due to tension and there's a force of gravity acting on it. And that's about it. All right. So we can go ahead and we know from that since it's accelerating downward, it's probably going to make more sense than anything to decree down is positive for this. So we can write F net equals MA and take the y component of this. So we'll have gravity down, tension up. This will equal MA. So mg minus t equals MA. And that's about as far as we can take that for the moment, so I'll just stick a star next to it. All right. So now let's go and look at the disk. So for our disk, let's draw an extended free body diagram for it. So there will be a force being applied due to the axle on the object. There will be a force of gravity acting on it. We don't know either of these, and there will also be a force due to tension on the object, and we don't know that one yet either. So this seems hopeless until we realize that if we think about the rotation, so that although we do know the force of gravity, but we don't know the force of the axle at all. The fact that we don't know that force doesn't matter from a torque perspective because it's not trying to make it twist. The line of action goes right through the axis of rotation. So the torque due to the axle is 0, and the torque due to gravity is 0. We've only got a torque due to the string. So we can look at this and realize that the string is trying to make this thing accelerate, do an angular acceleration clockwise. So here it probably makes the most sense to just decree that clockwise is positive, just to take it from there. So we could just as easily write Newton's second law for rotations as the net torque equals I alpha. So let's go and take a look at that. So we had a torque due to the axle and a torque due to gravity. And then we just have left a torque due to the force of tension. That's equal I alpha. This is 0. That's 0. And those are 0 again because the line of action passes right through the axle. And whenever that happens, the torque is 0. All right, so we're left with the torque due to tension. Well, the distance between the axle and the application point, where the string just leaves contact with the pulley here, is just the radius, r. So we can write the torque as TR, and it's positive because I decreed clockwise to be positive. Since I said it out loud, I can do that. If I didn't, then it would be negative. But by doing that, that makes the angular acceleration positive, so I don't have to worry about extra minus signs. So this is equal to I alpha. Alrighty, so that doesn't look super helpful now, does it? Because although I've got a tension here, if I could, in theory, solve this for the tension here and stick it into there, but that leaves me with this alpha here, and that doesn't seem to help until we remember that we know that this point of this piece of string right here at the end, that would be also the same as the tangential acceleration of a chunk of mass right at the end. And then we remember that this would be that the tangential acceleration was equal to, that the tangential component of acceleration was equal to r alpha. And here, that tangential acceleration of this piece right here is the same as the linear acceleration of this block right here, or else the string would stretch. So here we can write that A is equal to R alpha. Okay, cool. So then alpha is equal to A over R. So now we can write TR equals I alpha, IA over R. All right, or T is equal to IA over R squared. Now here, it's probably going to be useful to go ahead and look back up in our table the moment of inertia of a disk about an axis going through its center. And when you look that up, the moment of inertia is 1/2 the mass of the thing, r squared, times A over R squared. Awesome. So it turns out it did not matter at all what the radius of the wheel was, only that it was a disk shape and what its mass is. But now importantly, we can take that result and plug it back into star up above. So plugging that into star, we had, mg, little mg, minus the tension, which we've now worked out as 1/2 big MA equaled little ma. All right, now we can go ahead and start solving for the acceleration. So we've got a little ma plus 1/2 big Ma equals little mg. We can group out an A. Little m plus big M over 2A equals little mg. Then finally divide through by the things in the parentheses. So little a is equal to little m times over m plus big M over 2g. So this turns out to be, little m was 5 kilograms. This will be over 5 kilograms plus 10 kilograms over 2. So that's 5. That's a half of 9.8 newtons per kilogram, which here we will recast as meters per second squared to get 4.9 meters per second squared. Awesome. Alrighty, so in the next set of videos, we will start to turn our focus towards equilibrium situations. Catch you on the flip side.